Hello everybody, how's it going? Welcome back to class, to 32 Computer Science 3200. Today, our lecture may go maybe 10 or 15 minutes long today because I am going to explain temporal difference learning, which is a really cool topic, and the Q-learning algorithm, which is the main point of the reinforcement learning for this term. And then I'm going to show you assignment 5, which will be due on December 1st. So let's get right into it and explain what temporal difference learning is and what we'll be doing for the assignment. So let me, I don't think my stream deck is working. How's the voice coming through out there? All good? My levels say that it should be fine. All right, so where am I? PowerPoint. All good, perfect. Thank you for confirming for me. All right. So today we're going to be talking about on and off policy learning, temporal difference learning, and SARSA and Q learning. So let me just get started by saying that all of this is explained chapter 5.4 to 5.6 in the reinforcement learning textbook. This is on versus off policy learning and temporal difference learning, SARSA, Q learning, all the algorithms and all the examples I'm about to give are in the textbook. So please, if you are not sure about anything in these slides and you want a little bit more information, please by all means go to the textbook. And also just realize that I'm going to be going through a bunch of concepts in this lecture, but trust me, at the end, the thing that I want you to know and the thing that I want you to implement for the assignment is not that complex. It's just taking the Q-learning algorithm and putting it into JavaScript. That's the assignment. And so we're going to go over a lot of stuff, and it's going to sound a little bit complicated at first, but trust me, it's pretty intuitive, and I think you'll understand it for the exam, and the assignment will be pretty easy, I think. So first, let's talk about on-policy versus off-policy learning. So recall the Monte Carlo exploring starts algorithm that we presented before. What was happening in that algorithm in the previous lecture is that we use the current policy to update values, and then we use those values to update that policy, right? So we are improving the same policy that is used to make decisions and guide the learning. So when that happens, when we use the same policy to generate the episodes that we are also then updating, that is called on-policy learning. Off-policy learning means that the method learns a different policy than the one that is used to generate the data. So for example, if we were trying to learn an optimal policy, but when we were doing the learning, we were using, say, random actions or maybe some human actions, then that would be called off-policy learning. So let's just have a look. This is what we looked at last time, so we can recall this. We have our Monte Carlo policy iteration. And what was happening was we have some value estimates. We have a policy. We are going to, well, what we learned was we generated an episode using that policy. We updated our estimates, and then we updated that same policy. And we update that policy and then use the new version of that policy to generate the next episode. So the important part here is that we generate the episodes based on the policy that we're also updating, and that's called on-policy learning because we're using the same policy. Let's say instead that when we went to generate the episode, we used random actions, right? Because we can do that. If you watch someone take random actions, you can still learn from the outcome of those random actions. So if we had generated those episodes with random actions, but then updated a policy that wasn't a random policy, then that's off policy. So the policy we form, the policy that we're learning over time, does not guide the episode generation. So that is the big difference, on policy versus off policy learning. Wink, wink, possible exam question. So on policy updates the same policy that it was using to generate the action. Off policy updates a different policy than the one that was used to generate the actions. This means that on-policy learning learns a policy that takes exploration into account. So it accounts for epsilon greedy, etc. Off-policy learning can have poor online performance, but it may result in better performance after learning. So these last 2 points here, this is going to kind of be the thing that when we end this lecture, I'll have an example and you'll understand what this really means after the example. So we're going to do a whole bunch more stuff, but we'll come back to this, okay? But since on policy uses the same policy that it's guiding the actions to do the update, then it takes exploration to account. And this is actually going to be a really important point by the end of the lecture. So on-policy control methods. We've talked about this a little bit. In on-policy, the policy is generally what we call soft. In a soft policy, what soft means is that the chance to choose every action is greater than 0. So a hard policy might mean that when you're at some state, you're going to choose always go left. That's a hard policy, for example. A soft policy means that your probability, so inside your policy, your probability of choosing action A at state S is always greater than 0 for all states and all actions. It's kind of like epsilon greedy, right? Sometimes we're going to take the greedy action, but sometimes we're not going to take the greedy action. As it learns, this policy is going to move toward some deterministic optimal policy. One example of on-policy methods is to use epsilon greedy to select actions. Okay, so epsilon greedy is an example of a soft policy because we always have at least a chance to take any of the actions. So epsilon greedy on policy control. We talked about this already, but with probability epsilon, we choose a random action, right? That means that, so let's say epsilon is 0.1. So with 10% probability, we choose a random action. That means that, well, if we have a 10% chance to choose a random action, then we have a 90% chance, or 1 minus epsilon, to choose the greedy action. So in an epsilon greedy soft policy, this means that non-greedy actions have probability epsilon divided by the number of actions. So this is the size of the set A of S, which is the number of actions. And I'll do an example of this in a couple of slides. So if you have, well, yeah, I'll do an example of that. And greedy actions have probability 1 minus epsilon plus this. Because if you're doing a random action, you still have a chance to choose the greedy action, right? So this is an example of an Epsilon-Soft policy, which means that for every action at every state, the policy is greater than epsilon or greater than some value for all S and all A. So Monte Carlo generalized policy iteration Epsilon-Soft. That's what we talked about last time. We just hadn't defined it as this. Oops, I went back a slide. So on policy, Monte Carlo still follows generalized policy iteration that we talked about last time. We used first visit MC to perform policy evaluation and estimate the values of the current policy. Without exploring starts, if we simply made our policy greedy, right, we would never explore and many of these state action pairs would go unvisited. Epsilon-Soft on-policy methods ensure that exploration occurs and all state actions get visited, right? So by making sure that we always have a chance, even if it's small, of taking any action at any state, it means that as we run, millions and millions of iterations, we eventually visit all state action pairs. However, and this will become more obvious why this is the case at the end of the lecture. So if you don't understand this right now, we will do examples later. The policy that we learn is now only optimal within all Epsilon-Soft policies. But in practice, it's still quite good. And what this means is the policy that we learn takes that random exploration into account, right? So We'll get to an explanation, but it doesn't make a lot of sense yet. But I just want to present this now so that when we get to the example, you'll understand it better. So on-policy methods update the policy with the randomness of the epsilon greedy included. If the environment has hazardous features with strong negative rewards, then epsilon greedy will encounter them. And this is going to result in a policy that can be overly cautious and not globally optimal, right? So just think about it. If someone told you that in real life, as you're walking around, you have like a 1% chance that every step you take is going to be in a random direction, well, you'd probably change your policy, right? Because if you have a random chance of turning right, you're probably not going to be walking very close to the street, for example, or very close to a cliff. And actually, we have an example at the end of the class which shows the difference between our two main temporal difference learning algorithms where this becomes very obvious. So here is, again, we talked about this a little bit last time, but we're going to show it in algorithmic form now, which is on policy, first visit, Monte Carlo with Epsilon-Soft action selection. So our initialization is the same as before. We're going to have some initial value, maybe 0, for all of our state action values estimates. We're going to have a policy for, and this is an equally, maybe we just take a random policy at the start, but this tells us our probability of choosing each action at each state. And then we repeat forever, however long we want to do the learning. We generate an episode using our policy. Then for each tuple, state, action, reward in the episode, we talked about that in the last lecture. We calculate G, which is the return, which is the sum of the rewards following the first occurrence of this state action pair in the episode. And then we're going to update our value estimates, right? Last time we used the average, but this time we can use the incremental update step size rule. Remember, we had those two different update rules. We can use any update rule we want here, so let's just use the step size one. So now we have our updated value estimate, which is our updated belief of how good it is to take action A at state S. That's all QSA is. Then we want to do the policy updates. We want to change our policy to be greedy, but epsilon greedy with respect to the best action. So for each state in the episode, we're going to calculate this A star. A star means the best action, not the A star algorithm. And so we look over QSA, we look at all the values of A, and we choose the maximum value, okay? Then for each action A, in A of S, the actions that were legal, we say if A is one of the maximum actions, the probability in my next policy update of choosing this action is 1 minus epsilon plus epsilon divided by the number of actions. That's the formula we just talked about. Otherwise, then it's not a greedy action. So we just say that the probability of choosing an action at a state is epsilon divided by the number of actions. Now, we're about to do a numerical example of this so you'll understand it. Before we do that, just realize that, we're going to be operating in an environment like this. We've seen this environment a number of times. So we have some actions. We can move up, down, left, and right, for example. So here we have 4 actions. Okay, so we might have action 0, up, action 1 down, action 2 left, action 3 right. So here's an example Epsilon-Soft calculation. This is the formula that I just put in the slides. So we're just going to do one example of this so you know what I'm talking about. So let's say, for example, we have epsilon is equal to 0.1. So we have a 10% chance of choosing a random action. And the number of actions that we have is 5. So there's 5 legal actions. So let's just say that at some point, our QSA, that's our current value estimates of doing action A at state S, have these values, right? So the first action, whatever it is, has value 10. The second one is 20. Third is 15. Fourth is 5. And the fifth is 10. So we can see here that we have one maximum action, right? And that is action 1. So the index of the best action is 1. That's what A star is going to be. So when we go to update our policy, what we're going to do is say we're going to use these formulas to calculate the probability that I want to do those actions. So here are those probabilities. For each non-greedy action, it's just epsilon divided by the number of actions, right? So 0.1 is epsilon, 5 is the number of actions. So for all of my non-greedy actions, so 0, 2, 3, and 4, I'm going to have 0.1, which is epsilon, divided by 5, right? If I have a 10% chance to choose a random action and I have 5 actions, that means each of my actions has a 2% chance of being chosen. That's pretty obvious. However, the only other case is for the greedy actions, which get the additional chance of being chosen of 1 minus epsilon, right? So think about it this way. If I have a 10% chance of choosing a random action, that means I have a 1 minus epsilon, or 90% chance of choosing the greedy action. So if I have a 90% chance of choosing the greedy action and a 10% chance of choosing a random action, then I have a 90% chance of choosing the greedy action and a 2% chance of choosing any action. But because randomly we could also choose the greedy action, then that is 90 plus that 2%. See how that works? So we have 2% for every action because it's 10% divided by 5, and then that also gets added to the 90% chance of choosing the greedy action. So that is Epsilon-Soft. We have a non-zero chance of choosing anything, but we're also choosing the greedy action more often. Okay, so you see, hopefully that's a little bit more obvious now what these formulas mean. So, off-policy methods. Conceptually, they're pretty simple. Here is the learning control methods dilemma. We want to learn action values based on what we currently believe to be optimal behavior, right? So there's some optimal thing out there, and we want to learn the value of that optimal thing. But exploration versus exploitation comes back again. Because in order to find the optimal behavior, we need to behave non-optimally, right? So we need to explore in order to find the optimal behavior. But of course, the optimal behavior is not exploring. The optimal behavior is like a set path, right? But we need to explore in order to find it. So when we're doing on-policy things, on-policy Epsilon-Soft methods is a compromise. We find a near optimal policy, but that policy still explores. So how could we solve this problem, right? Well, let's use two policies. Instead of on policy, where we have a single policy that we use to both generate the exploration and end up with at the end, we're going to use two policies. One is called the target policy. That's the policy that we are learning over time, right? That's the policy that we're going to end up with. And then we have a behavior policy, and that is the one used to generate the episodes or do the exploration. So learning data from off of the target policy is called off-policy learning. So on-policy methods, in general, the implementation of them is a little bit simpler, okay? Because they're on policy, you only have one policy, you use the same policy to generate the episodes that you're updating. So they're a little bit simpler. Off-policy methods require some additional concepts. They have a little bit higher variance and they have a little bit slower convergence rates, but they're much more powerful in general. On-policy methods, we can consider those to be a special case of off-policy methods where both policies are the same. Okay, so that is on-policy and off-policy. Now what we're going to do is we are going to talk about temporal difference learning. I'm not going to go into complete detail about temporal difference learning. I'm going to go over the high-level details and introduce the two algorithms that you will need to know for the assignment and for the exam. But, of course, Chapter 6 in the textbook is all about temporal difference learning, so by all means, give that a read for more detailed explanation. So temporal difference learning is a central idea of reinforcement learning. It is very, very, very powerful. It combines Monte Carlo and dynamic programming ideas in the following way. So like Monte Carlo, TD methods learn directly from experience without a model of the environment. So they do not need a model of the environment. But like dynamic programming, the updates incorporate other learned estimates without waiting for the final outcome of an episode. And they call this, in the book, they call that bootstrapping. And this relationship between temporal difference learning, Monte Carlo, and dynamic programming is pretty important. In temporal difference prediction, which is the learning problem, where we're learning the values, both TD and MC use experience to predict the value of a policy, right? So we take a policy and we want to evaluate that policy to predict its value. The difference between TD and MC, or the main difference, is that Monte Carlo methods wait for an episode to finish and then update all the values based on the final return of the episode. So we'll play an entire hand of blackjack, then we'll go back and we'll update the values. Or we'll do an entire pathfinding episode and then go back and update all the values. But temporal difference methods do not wait. They don't wait for an episode to finish. Instead of waiting, they update the values after each time step. So it's much more powerful. We don't need to wait for episodes to finish. So Monte Carlo updates use episode return. We looked at this already. So the value of a state is going to be updated to be equal the previous value of the state plus some step size alpha times the return minus the previous value of the state. So we've already gone over that. Temporal difference, instead of waiting for the complete return, it's going to use the reward plus the next state's value. So right here, instead of using the return, okay, it uses this as the target, which is the reward that we immediately got plus gamma times the state's value. Because if we think about it, the return is what the state's value is estimating, right? So if we've done a bunch of episodes, eventually that return should be encoded within this state's value. So why not just update immediately rather than waiting for the episode to finish? So TD updates immediately after transitioning to state ST+1 and receiving reward RT+1. And the target for the update is this value, okay? And this is called TD0, or one-step TD. In the book, they go beyond TD0. They actually have TD lambda, which is this parameterized algorithm that values things, based on this parameter. We're not doing that. We're doing one-step TD for this course. I'm not going too deep into temporal difference learning. So tabular TD0 for estimating V, which is the value of a policy. It ends up being a simpler algorithm than Monte Carlo, in my opinion. The reason it's a bit simpler is because we don't need to calculate a whole episode and then look at everything that was in the episode. We just do something and we update a value. That's it. So how does that work? So we have some input policy, and then we have the value of our states. That's some initial value for every state. I'm doing it for states here, but you can do the exact same thing for state value pairs, or state action pairs. Then we repeat forever, right? We get the starting state, which is initialize some starting state for the episode. Then for each step of the episode, we have, we figure out the action that the policy says to do at state S. We calculate the next state, which is just doing action A at state S. We get the reward, which is the reward that I get for doing action A at state S. And then my value, I update it immediately. That's it. I use the reward that I got from doing that action and the value of the next state, and I just plug this in. And then the state becomes the next state. There's no waiting for an episode. There's no calculating returns. There's no first visit stuff. It's just immediate. We do an action and we learn from it. So TD uses the next state value in our estimate. And if we recall from way back in that lecture about dynamic programming, we had these values, right? So the value of a state given a policy is equal to the expected value of the return following that policy, right? That's the expected value of the return following that policy. We also saw that that was equivalent, we did some derivations, to the expected value of the policy given the current reward plus the return at the next state, right? Because if we think about I'm at a current state, what is the return? Well, the whole point of dynamic programming was that the return is the current reward plus the value of the next state, which is the return of the next state. And so, since the return of the next state is being estimated by the value of the next state, as we go on, we learn more and more and more, the return approaches this value. So, Monte Carlo methods use the first thing as the target, which is the return. Dynamic programming and TD methods use this as the target. Okay? So dynamic programming use this one, TD methods use this one. So temporal difference learning combines Monte Carlo sampling with dynamic programming updates. And so there's kind of a good example here of this from the book. And I know there's a bunch of text here, but I'm just going to read it out because this is a very good example. And I'm just going to leave my camera here. There's a couple of things. So example 6.1, driving home. As you drive home every day from work, you try to predict how long it will take you to get home. When you leave your office, you note the time, the day of the week, the weather, and anything else that might be relevant. So say on this Friday, you're leaving at exactly 6 o'clock, and you estimate that it will take you 30 minutes to get home. That's the state value estimation. As you reach your car, it's 6:05, and you notice it's starting to rain. Traffic is often slower in the rain, so you re-estimate that it's going to take 35 minutes for then, or a total of 40 minutes. 15 minutes later, you completed the highway portion of your journey in good time. As you exit onto your off-ramp, your secondary road, you cut your estimate of total travel to 35 minutes. Unfortunately, at this point, you get stuck behind a slow truck and the road is too narrow to pass. You end up having to follow the truck until you turn onto your side street where you live at 6:40. 3 minutes later, you're home. So the sequence of states, times, and predictions is as follows, okay? So you have this. While you were at the office, you had 0 time elapsed. Your predicted time to go was 30 minutes. So your initial predicted total time was 30 minutes, right? As you reach the car, you notice that it was raining. And so you say, okay, it's slower in the rain. So you've predicted that you have 35 minutes left to go. So at that time, you predict now that you have 40 minutes total time. When you exit the highway, you made good time. So now you predict you only have 15 minutes left to go. And so you have 35 minutes total time. Then you got stuck behind a truck. So you're saying, okay, I got 10 minutes left. Now it's back to 40. Now I'm entering my home street. I know that I have 3 minutes left to go. So my total predicted time is 43 minutes. So what is it about this example that's really good? Well, if you were using Monte Carlo methods, you would not make any of these intermediate updates. What you would do is you would take the final time of 43 minutes right here. Then you would take all of your current value estimates and you would just pull them toward 43 minutes. That's it, right? So this, like when we dealt a hand of blackjack. If we won the episode of blackjack, we went back to all the states that we visited and we pulled our update toward winning for each state after the episode had finished. So this is Monte Carlo. wait for the whole episode to finish, and then once the episode is finished, we take that 43 minutes and we update all of our value estimates that we had to be closer to 43 minutes. But what temporal difference learning does is at each state, it sees what happens. It sees that reward. And it updates our value estimates at each state based on the current information, not the eventual final outcome. Okay? And this ends up being much more powerful than Monte Carlo methods. Now, if we run infinite simulations, right, infinite iterations, they will both converge to the same thing, but typically, temporal difference learning methods converge faster. Okay? So this is a good example of why Monte Carlo methods may not be preferred to temporal difference learning methods. So what are some of the advantages of TD? Well, TD and MC do not require a model, so that's a big advantage. Monte Carlo waits until an episode is finished to do an update, whereas TD is online and incremental. Sometimes episodes are really long. Sometimes it's annoying to calculate the return of episodes, and continuing tasks have no episodes. So TD can take care of all this. And TD methods tend to converge faster than fixed size alpha Monte Carlo methods. In practice, this is true, but as of the time of me writing this slide, there was no proof for that. So that's TD prediction, which is updating value estimates. How do we do TD control? Well, we've discussed TD for prediction, which is given a policy. What is the value of that policy at a given state? How do we now update the policy? Well, we just follow GPI. We've already talked about GPI. So like Monte Carlo, we have the same exploration versus exploitation trade-off. And like Monte Carlo, we also have on policy and off policy. So on policy, TD control. In on policy, we need to estimate Q pi of SA for the current behavior policy pi and for all state action pairs, right? We want to visit all state action pairs in order to estimate the value of each action at each state. We can use the same TD method discussed previously for estimating V pi of S, but we can use Q instead of V. We know the difference between Q and V. And then all we have to do is update the policy pi to be greedy with respect to Q pi of SA. That's it. It's the same thing we looked at. Once we have the new estimates, we just update our policy to be greedy with respect to those estimates. So the first of two algorithms is called SARSA. SARSA, the algorithm. So this is on policy TD control. Remember, episodes consist of state, action, reward. So we have a state, we take an action, we get a reward. We're at a next state, we take another action, we get another reward, etc. Previously, we learned for TD to transition between episode states and update V of S. Okay, this is the formula that we had. And so we can translate that from state estimates to state action pair estimates really easily. We've already looked at this. And so this is what we have. So instead of state estimates, we now have state action pair estimates. And this is the SARSA algorithm. It's done. This is it. This is SARSA. So the updated estimate, after we get a sample, we take Q of SA at a time step t, and what we do is we take the previous value, we add our step size, we're going to multiply this by step size alpha, and we just have the reward from doing action A plus gamma times the, sorry, I've butchered this. Let me restart this line. The way we're going to update our state action pair estimate is with the same value, or the same formula as here, just with state action pairs. So we just take the reward that we had from doing this action at this state, then we add gamma times the estimate at the next state. So we calculate the next state, we look at the value of the next state, and we multiply it by gamma, and we add it. Then we subtract the previous value of QSA. And that's it. That's SARSA. You just have to do this formula update rule. So there's the formula update rule. And if st+1 is terminal, then the value of it is 0. The policy update is greedy with respect to QSA, meaning if you want to do the policy update, you just take the greedy action. And the formula makes use of the following things. So if we look up here at the formula, we use st, at, rt+1, st+1, and at+1. And so we have state, action, reward, state, action, SARSA. That's the SARSA algorithm. That's it. So SARSA using epsilon greedy, here's the entire algorithm. We have our current state action value estimates, and then just we keep repeating if there's episodes or it's a continuing task. We have a current state, that's the starting state for an episode or the current state that I'm in. We choose an action at state S using epsilon greedy on all the actions. Then we repeat for each state of the episode. The reward that we get and the next state is just taking the action A at state S, which gets us the next state and the reward. Then what we do, this is SARSA's little extra step, is we choose A prime from S prime. So we look at the next state and see what we would do at the next state. That is A prime. That's the next action using epsilon greedy again. And then based on the current state, the current action, the reward, the next state, and the next action, we just do this update rule. And then we set our current state to be the next state and our current action to be the next action. And that's it. That is the SARSA algorithm. It is remarkably simple to implement. All right. The next algorithm, which is called Q-learning, is off-policy TD control. And this and SARSA, I'm going to compare the two after I finish this part. So off-policy TD control using Q-learning. This was invented in 1989, and it was an early breakthrough algorithm in reinforcement learning. It's an off-policy TD control algorithm, and it's very, very similar to SARSA, except we don't look at the next action from the next state, except what we do is when we calculate the next state, we look at what we would do in that next state, but the best action there. So in SARSA, if we choose the action that our policy says to do at the next state, but in Q-learning, we instead look at all of the actions at the next state and choose the maximum one. That's the only difference between Q-learning and SARSA. So the learned Q value directly approximates the optimal Q value, which is the optimal action value function, no matter which behavior policy is being followed. So if we want to use Q-learning, if we want to do Q-learning using epsilon greedy, well, here's the function for that. It's actually simpler than SARSA. So QSA is the initial value for each state action pair. Then we repeat. S is the initial state, same thing as SARSA so far. A is the action that we choose at state S using epsilon greedy. We do action A at state S and get the next state and the reward. And then we don't even need to look and choose the next action. We just look at all of the actions at the next state and choose the maximum valued one, and then plug that into the formula. That's it. It actually has one fewer steps than SARSA does. And that's the algorithm. This is the algorithm you are going to be implementing for assignment 5. It's actually quite easy to implement. So Q-learning is off policy. But why is Q-learning off policy? If the algorithm estimates the value function of the policy generating the data, then the method is called on policy. Remember, SARSA learns the value of its policy, which does some sort of exploration. So SARSA is online. But Q-learning learns the value of a policy which does not explore, since it takes the maximum action value at the next state. Okay, so let's just go back real quick. What happens with SARSA is that we look at the next state and we look at the action our policy says to do at that state, right? And then it updates the policy based on that. So it is using the same policy to generate the episodes as it is now updating. However, with Q-learning, we're taking the maximum of those values. Not what the actual policy says to do, but the maximum one. No exploration when it updates this. So Q-learning learns the value of a policy which does not explore, since it takes the maximum possible action. Okay, now here's the example that they use in the book, and I really like this example because it explains the difference between SARSA and Q-learning really well. So keep in mind that when you do reinforcement learning, there are two phases to solving the problem. One is the learning phase, right? Where you constantly do things, you constantly learn, and you update your values, you update your policy. There's the learning phase. Then at some point, you have produced a policy, and that's your policy, right? You want to follow that policy. You know, your boss comes to you at work and says, I want you to use reinforcement learning to solve this problem. So you're going to go off, you're going to do a bunch of training, and you're going to figure out a policy. You're going to take that learned policy and you're going to hand it to your boss and you say, here's the optimal policy. So there's two stages. There's training, and then there's after that when you just have a policy and you use that policy. And this is going to explain the difference between those pretty well. So here's the cliff. You've got a grid world example. You're trying to get from the start to the goal. But between the start and the goal is this cliff. Okay? Now, I'll come back to this, but I want to read the rules. The actions in this grid world are moving up, down, left, and right. You're going to get a -1 reward at each time step. But if you step onto over the cliff, you get a reward of -100 and you go back to the start. So, what does that mean? It means that whenever I'm moving, I'm getting a reward of -1, right? Because I want to find the shortest path from the start state to the goal state. But if I'm right here, if I move to the right, I get -1 as a reward because it's taking one step. But if I move down onto the cliff, I get -100 reward and I go back to the start. Okay? So that is the cliff example. What's going on here? Well, if you are SARSA, what is happening is that as you are learning, you are updating the same policy that you use to explore. So if you're using Epsilon greedy with SARSA, as you probably will be, then as you explore, if you're here, for example, you might have a 10% chance of going off of the cliff, which is terrible, right? So what SARSA does is it says, okay, I'm learning the policy that I'm using to generate the episodes. So what SARSA will do is try and avoid being close to the cliff. Because if you're here, for example, with SARSA, oops, let me get my laser pointer. If you were right here, okay, SARSA, let's say we're right here. What SARSA is going to do is say, look at the next state and choose the action that I would do at the next state. So let's say I've chosen to go right, okay? It's going to say, what is the action that I would choose to do here? But that incorporates Epsilon greedy. So some of the time, it will choose to go down. So SARSA is going to think that the value of this state is pretty low because some of the time from here, it falls off the cliff. Okay, so what SARSA will do is it will value this state lower than this state because this state will lead to you falling off the cliff with Epsilon greedy more often than this state, right? Because if you go down here, you just go to this state. You don't go all the way to the cliff. But what Q-learning does is when it looks at the next state, it doesn't say take Epsilon greedy into account. It says, look at the best action you could do at that state. And so the best action at this state is certainly not walking off the cliff. It's moving to the right. So it takes the best thing, not the exploration thing. So what SARSA will end up doing is SARSA will learn to take this path all the way around and avoid being near the cliff, because SARSA is learning the policy. It's learning the values for the policy that incorporates the exploration. But because Q-learning is saying, no, don't learn the exploration part. I want you to learn the optimal thing to do at the next state. So this example is designed specifically to show the difference between Q-learning and SARSA. Their online performance. So online performance means during training. So look at this. This is an example. Let's say you have epsilon greedy with epsilon equal to 0.1. What this graph shows is that online, meaning during training, SARSA performs better than Q-learning. So here's the number of episodes that you do, and here's the sum of rewards during the episodes. So the sum of the rewards for SARSA during training is actually better than Q-learning. Well, why the hell is that? Well, it's because Q-learning is learning the optimal thing to do. So Q-learning is saying, I should be following this path. But during training, even if you're using Q-learning, sometimes you are actually exploring, right? So Q-learning is learning that this is the best thing to do, but it's off policy. The thing it's learning, the thing that it's learning to do, the policy that it's learning is not the policy that's generating what to do. So while Q-learning is following right along the cliff, which is optimal, it is also exploring and falling off the cliff sometimes. But SARSA is generating this suboptimal policy because it knows that it's also exploring. So if you train two things, one with SARSA and one with Q-learning, during training, SARSA is going to do better. But once you have your policy that you're going to hand off to your boss to use in production, would you rather hand the boss the SARSA policy or the Q-learning policy? Well, you'd rather hand them the Q-learning policy, because if you aren't doing any exploring, and certainly in production you're not doing any exploring, you're just taking the best policy, Q-learning comes up with the better policy in the end, even though while it's learning, it's doing worse. So I hope that makes a little bit of sense. That took a little while for me to understand the first time. So if you don't understand it right now, the book also does a great job. So Q-learning learns the values for the optimal policy, which is the policy which takes you right along the edge of the cliff, okay? This results in sometimes falling off of the cliff in training, because in training, it still does epsilon greedy action selection. SARSA takes epsilon greedy action selection into account and learns the longer but safer path, because it's on policy. It's learning the values of the policy that's guiding it. So even though Q-learning learns the values of the optimal policy, its online performance is still worse, okay? So this graph is important. The eventual policy of Q-learning ends up being better, but during training, it does worse. So this is kind of frustrating if you want to work in reinforcement learning, because while you're training, you might say, oh, look at this, SARSA's way better. But what you actually have to do is take your policy and just run it for a bunch of time steps without any exploration to actually evaluate how good it is. All right, so for exams, you could be asked, what does it mean to be on policy or off policy? Why is SARSA on policy? Why is Q-learning off policy? Why do SARSA and Q-learning produce different paths through the cliff? TD methods borrow from both MC and DP. What are they? And know the SARSA and the Q-learning algorithms as well. And remember, SARSA and Q-learning, they differ in just one term. So if you know one, you probably know the other. All right, so that's the lecture. Now we are going to go into the assignment. So the assignment is right here. So the assignment is a grid world pathfinding. So it's a really good example of how powerful Q-learning can be, okay? So we are going to be implementing Q-learning for a grid world pathfinding assignment. And here is the assignment. in this assignment, we have a continuing task. So it is not episodic. You have an agent right here. This blue circle is an agent, and that agent is in an environment. If I right click, I can move the agent within the environment. Okay, so that's what I'm doing right here. This environment has a few different types of tiles in it. So in this assignment, unlike assignment 2, where the colors didn't really mean anything, now they actually mean something. So a white tile is a tile that you can actually walk around in. A gray tile is a wall that you can't traverse through. And a blue tile is what I'm calling a terminal state. Now, it's not terminal in the sense that this is an episode that terminates. I'm just calling it a terminal episode because when you get to a terminal tile, what happens is on the next time step, you will be teleported to a random place on the map. The goal of all of this is to implement Q-learning so that you end up with something that looks like this. I'm just going to do the training. That happened very, very fast. We'll talk about exactly what was happening there. And what we end up with is the optimal policy. Okay, so if you see here, the policy is represented by the arrows within each of the grid cells. And so this right here says, the goal is to get the highest reward. And in this example, taking any action gives you a reward of -1, except going toward a terminal state here gives you a reward of 0. So it is desirable to go toward a terminal state. Now we can modify all of these values. I'll get into that in a little bit. But basically, we want to get to the states of the environment that have the highest reward, and we do that by finding the shortest path to them, right? So minimizing pain is maximizing reward, and the reward at each time step is -1. So what we see here is that if I go through and I do a single iteration, we will go towards the terminal state, and then we will teleport to a random place on the map. So this will go here, random place on the map. And so the policy that we learn does that. It's the optimal policy which leads us to those terminal states which have the highest reward in the fastest amount of time. Okay, so, but let's go back to what we started with. What we start with is an equiprobable random policy. Okay, so going up, down, left, or right with equal probability. Now, that over time will change as we iterate and we take more and more samples and update our values, etc. So let's explain the interface in full before I go on. As I said before, I can right-click to get to put myself into the grid. I shouldn't have clicked there. The right-clicking doesn't have all the bounds checking and stuff. So I can go anywhere in the environment. If I hit single iteration, what will happen is my agent will take an action from the policy. So for example, here it says move up, down, left, or right with equal probability. So it will take a random one. And then what will happen is it will move in that direction. It will update its internal QSA values, and it will update its policy. So you can see here that the policy has been updated. And it said, I don't like going in that direction because that gave me a -1, for example. Now here, the same thing. I will choose a random value here. Now let's say we were back at that place and I would choose another random value and then another random value, etc., etc. If I ever want to see what my values are, actually, let me show you this first. You can choose different environments. Let's go to the mini environment because it's a little bit easier to see. So if I click on any of the tiles in my environment, whatever is currently selected by mouse mode will be the thing that's activated. So by default, we have print values. So here, for example, if I click on this tile, you will see the reward that you get for arriving at that tile. You will see the current value estimate for that tile, and you will see the current policy at that tile. I can also do things like insert a wall there. I can clear the tile. I can insert a terminal state there if I want. I can set the reward. So maybe I can have the reward be 100 at that, or I can move the agent to the tile. So we have a nice little UI for doing that. So let me reset all of this. So here we have the parameters for our algorithm. We have alpha, that is the learning step update. We have epsilon, that is the amount of time we will actually be exploring. We have gamma. I'm just going to set this to 1. We'll just leave gamma as 1 for this assignment. And we have iterations. What iterations does is if I say toggle iterations, then 60 times per second, it will do this many iterations. Okay? So if I set that to 1,000 to 100, it's doing 100 iterations every frame, essentially. So the higher I put that, the faster my learning happens. If I go to the large environment and I pump this up and I hit toggle iteration, then you'll see that the learning should happen pretty quickly. Okay? So that's the user interface. Let's show what actually happens now. So up here, for example, in the top left, I have printed the values, which come down here. That might be a little bit small. Apologies for that. But you can see that the reward for getting to this state is -1. The values, I believe the order in which I list the actions are up, down, left, and right. We're going to test that in a second. So the values initially are all 0, and the policy initially is all equiprobable random, meaning that I have 4 actions. So with 25% probability, I'm going to choose any of those actions. The legal actions in this environment are up, down, left, and right. However, unlike assignment 1 and assignment 2, moving up here is legal. Moving right here is legal. So if you move up or you move into a wall, that's a legal action, except you don't go anywhere. So if I choose to move to the right here, what happens is I get my reward of -1 and I just don't go anywhere. So you can still move to the right, but you're just trying to move to the right. You don't get it. Okay? So let's do a single iteration here and see what happens to my actions. So I'm going to choose single iteration. So what I chose is I chose the action right. And what happened was, if I click here, I'm going to print out, oh crap, sorry, let me do that again. I had the wrong thing selected. So I'm going to choose a single iteration. I want to choose one where I'm going in a direction that's not blocked. Hang on. Okay, so I chose going down randomly, right? So I chose going down. Now if I look at my values, you can see the updated values of each action. So the first one is up, then down, then left, then right. And you might say, well, why is down -0.1? Well, it's because if we go look at the Q-learning formula, it's the previous value times alpha, or plus alpha times the reward, minus the previous value, but it was 0. So what happens is, if my previous value was 0, and my reward of doing that action was -1, that gets multiplied by alpha, and so my new value is -0.1, right? So since that going down now has a negative value, well, that's below all of the 0 values of all the other actions. So when I go to update my policy, I'm going to choose all of my maximizing actions, which is up, left, or right, equiprobable random. So I have a 1/3 chance of going up next, a 1/3 chance of going right, and a 1/3 chance of going left. Okay? Similarly, let's say I do it like this. Let's say I place my agent right here, and I am going to set the reward of this tile as 100. So if I move to this tile, I'm going to get a reward of 100. Now let's do a single iteration. Hopefully it goes down. If not, we'll just do it again. So I chose to go right. So now the value of this state has right as -0.1. Okay, let's go back here and choose another iteration. So it's going to choose randomly from up, left, or down. It chose to go up, and it's a legal action. It just didn't make me go anywhere. So now the value of going up is also negative 0.1 because I got a reward of -1 for doing that times alpha. Okay, let's take another action here. Finally, I chose to go down, right? So the value of going down is the value of the reward of reaching the next state, which is 100 times alpha, which is 0.1. So the value of going down here is 10. So now you can see that the policy has been updated to say, well, I really like going down here, so I'm going to go down here. So that's the very simple thing that's happening. You're going to take an action. So you're at a state. Let's say we're at this state. We look up our policy and we say, what should I do at this state? You're going to choose one of those actions. After you've done it, you get a reward based on the state that you ended up in. You're going to use the Q-learning update rule to update your values, and then you're going to update your policy. And all of that is reflected for you in the UI. So you can go around and debug it like that. So if I do this, and the color, so let me explain the color. White means 0. Red means it's below 0. Green means it's above 0. So what I've done here is I've just colored it so that it scales the redness or greenness based on the maximum value of anything in the thing. So if I keep toggling here, let's put this up to, here we go. Okay, so what I see here, my values end up being very close to 100. And the reason is because the value of this state is the expected return following my policy in this state. So if my policy says go left, then go up, right? Then this is essentially 100 minus 2, so it'll be close to 98 as we converge. If instead I leave this as 0, then what I will get is, well, I'm not going to have any green values because I don't have positive rewards, but I will see up here, for example, that what my value of going in a specific direction, if I leave the reward of the goal state as 0, is essentially the distance to the goal. So if I think about it, the distance to the goal is going to be just simply like -1 reward, right? So if my distance to the goal from here, let's look at it. So the value of going up is -1.9, which is almost 2. Because the distance to the goal would be, okay, going up, -1 reward, then I go left, -1 reward, then I go down, 0 reward. So if I go up, I'm 2 away from the goal. Here, this is saying that the value of going up is -1 because I'm 1 away from the goal. The value of going down is 0 because I would be right at the goal. The value of going left and the value of going right are both close to -2 because I would essentially be putting myself 2 away from the goal. So if you keep the reward of the goal state as 0, then your value estimates are essentially equal to the shortest path. And that's pretty much the interface. And if we go here, let's just look at it again. If I do this enough times from enough different places, okay, let's just speed this up a bit. What I end up getting is the optimal path. Now, the large environment takes a while to converge. Let me go back to the default. There we go. So the default one has converged, but watch this. If I put in a new terminal right here, then as we keep learning, it'll update the path in real time to reflect, oh, there's new things here. Like I should probably be heading toward these. Okay? Or if I put in some walls while I'm learning, then, oh, that wasn't a very good example. Let's say these over here say I can go to the right, but if I block this off, then I can no longer go to the right. So like as I'm modifying this thing in real time, it's updating the policy to be up. So that's really cool. That's a really cool thing about reinforcement learning. Okay, so now that we know what the user interface does, let's dive into the code, as we always do. So here is the code. You're going to have several files, as you usually do. You can ignore the GUI and the RL GUI and the index, and the high charts thing, that's the graph. Oh, and what the graph is doing here is it's showing you that over time, as you're learning, the average number of iterations, meaning actions, that you have to take in order to reach a goal is going down. So that's just showing you that, yes, your policy is improving over time. So the first thing we're going to look at is maps. So Maps.js contains all the different map data. So as we saw before, there are 3 different types of tile. There's a clear tile, there is a wall tile, and there is a terminal tile. So if we look here, for example, the default map has a bunch of C, those are the clear tiles. It has some Ws, those are the wall tiles, and it has some terminals, those are the T tiles. Followed by those are the rewards. So you get rewards by arriving at states, and so the reward at arriving at the terminal state by default is 0, but you could change that to whatever you want for testing purposes. And the reward for arriving at any other state by default is just -1. So we're just saying the reward from doing any action is -1. And this is just how I define the maps and how the user interface allows you to select between them. Okay, so if I choose these, all it does is load the different variable. Next, we have the Environment.js. So the environment class essentially holds all the data about the grid world environment. Okay, so it holds the width and the height, the actions that are legal. So that's going up, down, left, and right. I can get the type that's at a grid. So this would return C, W, or T. So that would be the type of tile, whether it's clear, terminal, or not. I have a thing here which is get next state. So I implement this for you. You do not have to implement the getting of the next state. So you pass it in an X and a Y and the index of the action, and it will tell you what the next state is. So that'll return the next state. You have get reward from a state. So once you land on a state, you want to know what the reward of that state is or what that action was. So you can get the reward right here. You can get the values of states. You'll probably never use that. You can set the type, set the reward. That's all used by the GUI. The sets, you're not going to use the sets. Get actions, so you are going to use that, so you're going to need to know the actions. You might need to know whether it's out of bounds, blocked, terminal, etc. So the environment.js stores essentially the whole environment. It stores the grid of values that you need to use for that. Okay, next we have the final thing, actually, which is the RL student file. So despite how complex this looks, it's probably going to be the easiest assignment, I think. So let's go over this and all my notes that I've written for it. So let's close this and then I'll make this bigger. And once I'm done this, you'll know how to do everything for the assignment. So all of your assignment code has to go in here, blah, blah, blah. A very important note is that computed actions are represented by an integer. The integer is the index into the this.env.getActions array. Wherever we pass an action in this class, use the integer index, okay? So if we're passing around actions, we're not passing like 1, 0 for going right. We will look at over here, if we want to go right, we're passing in 3 because it's 0, 1, 2, 3, okay? And another note, and I've already explained this, terminal states do not actually terminate an episode. They simply teleport the agent to a random non-blocked tile on the map. This is because we are working with a continuing task, so technically none of the states are terminal. A tip is to complete the assignment in the order of the steps listed in learning iteration. So we'll get to that in a bit. First, we're going to look at our constructor and all the class variables. So we have the config. So the learning configuration is going to store all of the variables from right here, okay? So we have this.config.alpha, this.config.gamma, this.config.epsilon. That's what you're going to use to implement your algorithm. This.env, that's the environment, so that's how you get a hold of all that data. This.q is your value estimates. So instead of saying QSA, I've made it easy on you and it's just QXYA. So QXYA is the value of doing action A at state XY. So it's a 3D array. I've already set it up for you. You don't need to worry about that. And then the policy has the same format where the policy array of PXYA is the probability of doing action A at state XY. And then we have this dot state, which is the current location, the state of the agent on the map. And then it calls the init function. In the init function, what it does is two things. First, it sets all the QXYA values to 0, and it resets them all for you. And it also initializes the policy to be equiprobable with all of the actions. So if you want to, look at these for example source code for how to do your stuff, that's fine. I've done it for you. The Q values and the policy values are initialized for you. Here is where you're going to be doing most of your work. It has 7 steps, but those steps are quite easy in comparison to previous assignments. So this is the Q-learning generalized policy iteration pseudocode. Remember that the computed actions are represented by an integer. The integer is the index into the getActions array, and wherever we pass an action, use the integer index. So that being said, what is the first thing that you have to do? The first thing that you have to do is the following. So remember when I said that if the, well, let me go to the default. If the agent is at a terminal state, when we do our next iteration, it gets teleported to another random legal state on the map. So that's what you have to do first. You have to check to see if the agent is in a legal state. So it says while the agent is not in a legal state, so while this dot state is not legal, set it to a randomized legal state. And so you can use this.env.isTerminal or this.env.isBlocked to get that. And so a legal state is one that is not a wall or a terminal state. So that is the very first thing that you have to do, is make sure the agent is in a legal spot. If it's in a clear tile, then it's fine. You don't have to do anything. Next, select an action A to perform based on our current policy. This will be stored as the integer index of the action. So that is this.select action from policy. So I already have a function here for you, and this is that function. So this function should select an action to perform at a given state, given the current policy and epsilon greedy in this.config.epsilon value. So what do you have to do here? You take in the XY state and you return the integer, the index of the action to perform. So I've got here, I say max value action index is 0. Your job is to set that properly. So you choose the action based on epsilon greedy with the probability stored in the policy. Then PXYA is the probability of choosing the action A at state XY. And so what you are going to do is choose randomly from all of the actions which have the maximum probability and return its index. And we went over that in a previous lecture. Okay, so you have, you're going to say, for example, you're going to generate a random value. So R equals random between 0 and 1. If R is less than this dot config.epsilon, then this is where you choose a random action. Otherwise, you are choosing the greedy or one of the greedy actions. Okay, so that's what you're doing in this. It's a very, very simple function. The next thing that you have to do, and so literally what you can do here is you can say let A equal this dot select action from policy, and then you are using this dot state. Like that's all that's happening here. This function should kind of read as English. Next, calculate the next state by doing action A at state S. Well, look, we have this dot env dot get next state. Get next state takes in X, Y, and action index. So I can say let next state equal this dot env dot get next state. And then that takes in what? It takes in x, y, and action index. So that's this dot state 0, this dot state 1, and A. There, I've actually done step 3 for you. There you go. Then you get the reward from doing A at this dot state from the environment. The reward you get is the reward value of the next state. And you have this dot env dot get reward. So you're going to take that next state's x and y, and you're going to pass them in here. And then you'll get the reward from doing that. So you'll say let r equal, and you'll calculate the reward that way. Then you update the Q value based on the Q learning update rule. And we have this dot update value. So that's another function down here. So this dot update value takes in the state, the action, the reward, and the next state. And then you implement the Q learning update function, right? So you implement that, or more accurately, this. Okay, so that's what you implement for there. You just take that. I mean, you can take this and you can come over here and you can paste that in there. And then you can, it's this dot Q, it's action, it's XY instead of S, right? So you just modify that. You implement the Q learning update function. That's actually pretty easy to do. Then after you've updated the value, you update the policy. So this might be probably the trickiest part, where you call this dot update policy and you follow the details for updating the policy. Okay, so max action value equals get the maximum action from Q, X, Y, A. So you iterate over all the A's. The max actions are the actions which gave you the max value. And then for each action A, if A is in max actions, then you just divide 1 by the length. Otherwise, you have the probability is 0. Okay, so this is the greedy update rule for your policy update. And then you go back up and then you set this state equal to the next state. That's it. This is actually, I think, the easiest assignment, but also one of the coolest assignments, because it's pretty easy to implement and it's very powerful. Oh, these two last functions, they're used by the UI. You can pretty much ignore them. Actually, I may update it so that they're not even there. Just ignore that min Q and max Q. That's used by the user interface to do the coloring. So that's it. You just have to follow those 7 steps. And follow the 7 steps. A lot of it, probably too much of it, has been done for you already. But on your resume, you'll be able to say that you implemented Q learning from scratch in a dynamic grid world environment. All right, I think that's it. You should be able to take it from there. That's a pretty good explanation. And then if you set this to 100 and you click toggle iteration, you should see the things that are further away from the terminal states get darker, and you should see this line going down over time. All right, so that assignment will be released by morning tomorrow. And if we look here, you will have 16 days to complete that, and I think that's more than enough time to do that. So that's it for today's lecture. The last few lectures, we will be going into stuff like neural nets, and we'll be watching a movie, or you'll be watching that on your own, and all of that stuff will be on the exam. So thanks for tuning in, and I'll see you in the next lecture.